All right, Patrick, please go ahead.
Uh, Today we are going to see about unicast routing protocols. So unicast routing protocols means transmission between a single sender to a single receiver. So it's a point-to-point communication between sender and a receiver. So if we want to transmit a packet from a sender to a receiver, the set of routing protocol used in the router table to make entries to guide the packets to receive its destination in a group of network. It will be interior or exterior, that is intra-domain or extra-domain. So we will see about that. So the unicast routing protocol, unicast means it is the transmission between single receiver and a single sender. So there are also broadcast and multicast routings. So broadcast, there will be an one sender and multiple receivers, and multicast, there will be an multiple senders and multiple receivers. So this is the difference between unicast and multicast routing. So here there will be one sender and one receiver. There will be more senders and more receivers, and there will be one device to uh, it will send the data to one single device. In multicast routing, there will be one device which then sends the data to multiple devices, and it is a single node topology. And multicast, it will work on star mesh tree hybrid topologies, and it does not scale well for streaming medias. Unicast and multicast, it does not scale well across large networks. And in multicast, in unicast, multi unicast casting utilizes more bandwidth, where multicast utilizes bandwidth efficiently. And unicast is an one-to-one mapping, and multicast is an one-to-many mapping. So these are the differences between unicast and multicast routing. So there are these three are the common algorithms used in unicast routing protocols. So the first one is routing information protocol, that is RIP protocol, which is based on distance vector algorithm. So distance vector algorithm is nothing but it will transmit its distance vector to each of its neighbors in a routing packet and inform the neighbors about the topology periodically. So each router receives and saves the most recently received data about the distance vector from its neighbor, and it will recalculate the distance vector when it receives a different input or when the link breaks down. So the next one is the open shortest path, shortest first path first. So it is based on the link state algorithm. So link state algorithm uses the link state routers to exchange messages that allows each router to learn entire network topology. By learning it, it will compute the routing table, and by using the shortest path. Uh, that's it. So these both protocols based on the intra-domain. So intra-domain, it will calculate the routing tables, all these things within this network. So the process happen within the network comes under intra-domain. In inter-domain, it will be the data will transfer between two networks. So it will border gateway protocol comes under inter-domain. So interdomain. So the broad gateway protocol is based on vector algorithm, path vector algorithm. So the path vector algorithm, where the routing protocol, which maintains the path information, that will get update dynamically. So in that, the updates will discard the looping links and uh, other connections which are repeating. That is, if the data packets return to the same node, like itself, if it is happen like that, it will discard the link easily in this path vector routing. So these are the common algorithms we see in unicast routing protocol. So uh, for routing information protocol, it is an dynamic routing protocol which uses hop count as an routing matrix to find the best path between source and the destination network. So hop count is the number of router occur between source and the destination network. So there are two versions, that is RIP 1 and RIP version 2. So these are the versions of uh, routing protocol. There will be another version also, RIP PNG. So the update of the network or exchanged periodically, and the network information was always broadcasted. So the difference between RIP version 1 and RIP version 2 are it is uses broadcast traffic for updates, and it uses multicast traffic for updates. And this is does not send subnet mask to routing protocol, and it sends subnet mask to routing protocol. So by not sending the subnet mask, it is called as uh, classful routing protocol, and RIP version 2 is called as classless routing protocol. So here it is less secure and more secure, and it does not support for authentication, and it supports for authentication, and it supports classful networks only, and this supports both classful and classless networks, and it does not provide trigger updates, and it will provide trigger updates. So these are the some of the differences between RIP version 1 and RIP version 2. So for open shortest path first protocol, uh, yeah, there are some similarities also here. The distance vector, it is both are distance vector routing protocol, and both have the hop count limit as 15. So if it exceeds 16, it will count as infinity. So and the administrative distance for RIP protocols are 120. So for open charter spot first protocol, it is a link state protocol, routing protocol. This used to find the best path between the source and the destination, and there is no restriction such as hop count in OSPF. So it will calculate the metric in terms of bandwidth. It is more intelligent routing protocol than RIP protocol. So the administrative distance of OSPF is 110, and there are three types of tables present in this OSPF. There are neighbor table, database table, and routing table. So neighbor table contains the data about the direct routers which are directly connected in this network. It is also called as adjacency database. And database table, it contains information about all possible routers in network within the area, and it is also called as link state database. And the routing table, we know that it is used to contain, it will contain the list of best path to each destinations. So these are the tables present in OSPF. So for border gateway protocol, we have to know what is autonomous system. So it is a network or group of networks that are managed and supervised by a single organization. So yeah, uh, as it is a open standard and exterior protocol which is used by the router to inform to transfer information between different autonomous systems. The updates for the routing protocol are incremental and trigger. So if any of the connections get deleted or uh, change, it will trigger and update the routing table through that. So it is application layer protocol sends the updates to the manually defined neighbors as unicast. So in this Broadway gateway protocol, we have to mention the uh, routing tables to the neighbors manually. So it will be unicast. So the metrics for border gateway protocol is attributes. So these are the things we see in product gateway protocol. And this is the end of my presentation. Thank you.
Yeah. Thank you, Patrick, for the presentation. Thanks for your effort. I want to appreciate you. All right, so I have a few comments to make. If you want, you can mute yourself. However, if you want to respond, you can do that. It was a good presentation. Want to applaud along with your friends. The first observation is you have spoken about the unicast and multicast routing protocols, but in fact, they were the differences between unicast and multicast communication, okay, not the routing protocols. That is point number one. But that was well clearly explained, the unicast and multicast communication and the differences among them. The second one, you have spoken about the administrative distance. Which we haven't spoken earlier. Normally, this administrative distance is a measure of preference of route. For instance, there may be two routes to the same destination in a routing table. All right, so probably parallelly, I will share the screen as well, if I can open it. Okay, let it get ready. Yeah, while it is getting ready, I can give you the theory. Yeah, so when you have two networks, okay, it could be 1.0 network and the 5.0 network, and there may be existing two routes. Yeah, the packet tracer has come up. Just hold on. So I share the screen. I hope my screen is visible, but don't worry, I'm not going to use it to explain today. I have a PPT to make. All right. If you could see on the screen, this is the link which I have just created. Okay. The other topology is same we have seen yesterday. This is a link which I have just created between router 0 and router 2. Now let's take the case of this network 192.168.10/25 and 192.168.128/25. Okay. Now there are two networks. These two are interconnected through a multi-hop network. All right. Now from this machine, if you want to go to 1.128 network, maybe this PC, okay, from PC0 to PC3, if you want to go, there exists at least two routes. Okay, so you have to go this way, go to router 0, then router 1, and then router 2, then the switch, and then finally PC3. This is one of the routes. The other route is PC0, switch 0, router 2, switch 1, PC3. All right. So these are the two routes which are existing. Now the question is, this router has learned the routes, one through the static routing, the other one is through dynamic routing. Okay. For example, RIP. Okay. So the static routing has got this path. Okay, which means from router 0, router 1, then router 2, and this network. This is what learned through static routing. And RIP has learned this as the route. Okay, so from router 0, you have got two routes to reach 128 network. All right, either this way or this way. Now, which one should be taken? Apparently, we will think that this is the path which is to be taken. Okay, but I can ask you a question. If this link has got a maximum speed of 56 kbps, whereas this has got the speed of 100 megabits per second, or probably 1 gbps link, all right, now you would change your mind. No, sir, this seems to be slower. Probably I'll go for this route. Okay, now there is no single point. There is no single decision cannot be taken just by looking at the distance between the routers. Are you getting the point? Yeah, so we have to be careful which parameter is chosen. Now, when you look at the RIP protocol, RIP version 1 and RIP version 2, it takes only the hop count as the metric. So RIP straight away would say, boss, don't take this route. Router 0, router 1, and router 2 seems to be longer. Don't go for it. You go for this route. This is the shortest path. But it is not going to take into account the reliability and the bandwidth of the link. As I have said, this has the lowest bandwidth, probably this has the highest bandwidth possible. You would prefer this way. This is very similar to 6-lane highway. This is very similar to a single lane village road. has got lots of bumps and speed breakers and so on. Okay, so this is what exactly the problem the routing protocols are facing. So RIP protocol uses only the hop count as the metric, whereas the other protocols such as OSPF and other people, they use few other metrics, okay, as the parameter. And if you look at BGP, it uses attribute as the metric. I'm going to explain to you shortly that. All right, now I was trying to tell you about the administrative distance, right? So what is that administrative distance? When you talk about this connected network, the administrative distance is 0. When you take the static routing, the administrative distance is 1. Okay. If it is a RIP protocol, administrative distance is 120. If it is OSPF, I think it is 110. Forgive me if I'm wrong. Right. So lower the administrative distance, higher the preference. If there are two routes existing, one has the administrative distance of 0, the other has the administrative distance of 110, the router will obviously choose the route has the lowest administrative distance, that is 0 in this case. Okay, so administrative distance is not the priority, but it defines the preference of the routes when more than one route is existing to the destination. Okay, that is what Patrick was talking to you about, the administrative distance. All right. All right. Now the second one, he has spoken about the hop count as 15 in the case of RIP protocol. That is true. RIP protocol can support to a maximum of 15 hops. In the topology which I have just shared, we got probably 2 or 3 hops as the maximum distance. Okay, so the RIP protocol supports a maximum of 15 hops. Anything beyond RIP protocol would say, sorry, this is infinity, which means the routing information cannot be exchanged among them and your RIP protocol fails if the end-to-end hop count is greater than 15. That's why RIP says anything beyond 15 is infinity. You got it? All right, there are a lot of tweakings are also happening in the case of RIP protocols, route poisoning, what is that? Poison rivers, count to infinity. So there are multiple tweakings and enhancements are also available with RIP version 1, RIP version 2 protocols. It's my appeal that you will explore further on that. All right, so thank you, Patrick, once again for setting the tone. And he also has spoken about BGP and the autonomous system. So that has made my job easier today. He has introduced to you what is an autonomous system. Okay, it is a single entity which comes under a single administrative control, but the autonomous system can be huge or it can be smaller. There is no size, there is no hard and fast rule that it must be only this many computers, this many networks and so on. No, anyone who comes under a single administrative authority can be called as autonomous system. And we are also going to see why BGP takes the policy very seriously when it is doing the routing. We have spoken about the static routing, we have spoken about the dynamic routing, for instance, RIP and OSPF. We haven't spoken about the policies. Okay, but BGP, border gateway protocol, takes up the policy very, very seriously. So I have a few slides to present to you. So let me share my screen. But before that, as I promised yesterday, I'll also speak to you about IPv6 little bit before jumping into BGP. So I'll see whether I can wind up today. I assume that my screen is visible. All right, so I remove the headset. All right, so if there is any disturbance, any difficulty in listening to me, my voice, please, you can give a call to me over my phone. I have my phone with me. All right, so this is what the topic we have spoken yesterday about the ICMP protocol and how it works in your trace route and ping command and as well. So this we have visualized yesterday using the packet tracer. So continuation to that, we'll look at IPv6 as well a little bit. All right, but talking about IPv6 itself will take hours together, but due to time constraint and also the syllabus requirement, I probably give a small touch on IPv6 and go. All right, we all know the necessity of having IPv6. Very simple point. The primary point I would say is that the depletion of IPv4 address space, 32-bit address space is not sufficient to give IP address to every grains. Now you could see we are talking about the 5G networks. You talk about the bigger networks, all right, every device, especially when the IoT is born, the necessity of addressing, especially the IP addressing, has become inevitable, right? So that's the reason IPv6 was born. It is having the address space of 128 bit, whereas in IPv4 it is only 32 to a maximum of 2 power 32, whereas it is 2 power 128. So the IPv6 designers claim that every grains of this universe can be addressed using the IPv6. All right, there is not only the address depletion which has motivated the scientists and the researchers to come out with IPv6, but also there are few other additional motivations, as you could see on the screen. The header format to speed up the process. So they have found some limitation in IPv4 header format and its size, and they also have made minor enhancement in terms of to improve the quality of service. So if you do not know what is quality of service, point is very simple. A quality of service defines the parameters by which quality is measured. For instance, the quality of service parameters of network could be the speed, latency, throughput, reliability, availability, scalability, and so on, right? So these are some various parameters which constitute the quality of service parameters. So in order to improve the quality of service, also the IPv6 is introduced, all right? So IPv6 datagram format, in a nutshell, it is having a fixed size of 40 byte header. No fragmentation is allowed. What is the fragmentation? If you look at IPv4 header structure, you got some field called fragmentation offset, identifier, fragmentation offset, and then there is a flag bit just to indicate whether the further segments are coming or not. But no such fragmentation is allowed. So if your if your data link layer is not able to cope up with the speed, IPv6 says I don't mind, all right, because you have a parameter called MTU, that is maximum transfer unit. Based on that, these IPs are fragmented, if you remember that, all right. But whereas in IPv6 it says, boss, I'm not going to bother who you are, but I'm not going to do any fragmentation. It is up to you to improve your ability to forward the packets. Okay, so this is the IPv6 datagram packet. You got the version very similar to that, and there is a priority, just to give importance, very similar to how the ambulance is given more priority on the traffic. So you got this priority field, all right. And there is another field called flow label, which helps you to improve the quality of service, all right. Then the length of the payload, very similar to your IPv4. The next header, very similar to the upper layer protocol in IP header. Hop limit, the TTL field is changed as hop limit here. And then the major change is the IP address size. It is 128 bits in size. And then you also have got the data. All right. Now, what are the other changes? As you could see, the checksum is completely removed, with the sole reason that with the invention of latest technologies, the reliability has improved a lot. So it is felt, or it is also deduced, that the error rate in the communication link is very, very minimal, if not zero, right? And hence the checksum field is felt as if additional burden on the IP header. That's the reason checksum is removed. Please remember, your data link layer protocol also has got the checksum. TCP also has got checksum, and of course UDP as well. Hence the additional checking at the network layer is removed in order to improve the speed by which to enhance the quality of service. And the options fields, it is allowed but outside the header. So the header is a fixed one. You need not have a separate field for header length. Okay, and you also have got the introduction of ICMP version 6 has got some new capabilities. As you could see, some additional messages like packet too big and so on are included in IPv6, because that is very essential to indicate the center if something has gone wrong. Okay, now the question is, sir, if you look at the first line on the screen, it says not all routers can be upgraded simultaneously. Why can't this be done? The reason is, first reason is no flag day. Okay, which means if I am the network administrator, or put yourself into the shoes of the network administrator, you have got some 100 computers, some number of networks internally, right? And you are using ICMP version, IP version 4, and so far things are happening well. You are comfortable, all right? So end-to-end connectivity is established. There is no hiccup. You are able to communicate with the external world and so on. Now you can simply ask a question. Sir, why should I learn about IPv6? Why should I convert all the addressing space of mine into IPv6? Because I'm comfortable with IPv4. You got the point? So there are a lot of such reasons why IPv6 cannot be adopted simply like that. All right. Now the requirement is some of the people who can understand the benefit of IPv6 may opt for IPv6, whereas few others who are comfortable with IPv4 would have some hesitation to move towards IPv6. So how can we do that? Now, one simple solution is you better make both of them interoperable. That IPv4 can understand IPv6 and vice versa. All right. How can we do that? There are two things, but of course, in your textbook we have spoken about only one. The other one I'll probably give you the hint. One, the famous one is tunneling. All right. I can give you yeah, probably an anecdote or analogy. I'm not sure whether it exactly fits, but that is very similar to what I'm going to tell you. All right. A few years back, myself and some of my colleagues visited Cochin, and we could see some boats called ferry. If anyone of you are from Kerala, probably especially from Cochin, you can easily understand what I'm trying to tell you. All right. There are multiple places which are separated by big rivers. All right. So from this place to other side of the river, if you have to go in a car, it is not possible. It is possible. There will be bridges which may be 500 kilometers away. So instead of crossing and reaching in 100 meters, you have to go and travel along maybe 4 kilometers, 5 kilometers, take the bridge and then come in. That is going to be waste of time as well as waste of fuel as well. And then I could see some interesting carriers available which are called as ferry. That's what I was told. Some big boats which can carry the even the cars, bikes, the people and all the luggages. All right. So what happens? This ferry comes in and you are loading your vehicle. It could be a car. All right. And the ferry takes this car along with you others to the other side, and then it drops you there and you can go there. All right. So this is going to save your time. This is what exactly happening in tunneling. In other words, probably you have your motorcycle you are using in your native place. You want to transport this to one of your friends who is in Hyderabad. All right. You are not in Hyderabad, but it has to be sent to Hyderabad. All right. So you take the vehicle, put it in the luggage space, maybe in the train or bus or probably the transports, and then they take it in them and they drop there. All right. Now the vehicle, the two-wheeler, need not go on the road. In the previous example, the car cannot run on the water. All right. So on the stream, on the river, somebody else carry this. Very similar to that. You got IPv4. All right. And you also have got IPv6 packets coming. Now the problem is your IPv4 routers cannot understand the configuration or all the fields which are in IPv6. So what shall we do? Do the tunneling. What happens? You could see on screen. This is your IPv4 header. All right. So this is going to be your IPv4 header. And then as the payload, the IPv4 header has got the payload. What is the payload? All the data will be placed, right? So in the payload, you include your IPv6 points. Okay. So all your IPv6 header, everything, upper layer protocol, the application layer, everything becomes the payload of your IPv4 tunneling. So look at this as the lorry, probably the probably pink or orange color, maybe red color. That can be taken as the lorry or the vehicle or the ferry, and this payload, the blue color datagram, can be taken as the car which is traveling on this big vehicle. Okay, this is what exactly happening in tunneling. So what happens physically? There are IPv6 routers, but in between IPv4 routers. So this IPv6 packet cannot travel over IPv4. So what should happen? You are creating a tunnel. How can we create the tunnel? The two-wheeler, the car is coming till this, and then you carry this in bigger vehicle and then drop here. All right. The same thing is shown here. You got A to B, it comes as IPv6. From B to C, it becomes the payload of IPv4. And then it goes here. From here, it will get down and it will start working. This is what exactly happening in tunneling. The second approach is dual stack. In dual stack, these routers, for instance, this router or this router and this router, are expected to understand both IPv4 and IPv6. So they can carry both these packets. But there is a problem. For example, flow, which is one of the important fields, which will be lost when you convert this IPv4 into IPv6 to support the dual stack. Okay, so these are the two major options which we got to have interoperability of IPv4 and IPv6. How much time? Yeah, I have a few more minutes. I'll try to wind up with BGP. I'll go a little faster, but this will be easy concept. All right. So when you talk about the intra-domain routing or intra-autonomous system routing, we speak about RIP version 1 OSPF protocols. Now we come into inter-autonomous. What is an autonomous system? Patrick has just explained. The separate set of networks or the domain which comes under a single administrative control. That is the autonomous system. Okay. So now the point is, how can you connect two autonomous systems? So what's the big deal, sir? You can use OSPF, you can use RIP. That's okay, sir. But every individual network, every administrator or administrative control will have some different policies. For instance, a specific country may not accept all the traffic of Facebook or probably any of the social media, whereas some other country would block a specific search engine and so on. Right? So every have administrative control have separate policies. Now you are supposed to connect all of them to provide the proper internet connectivity. All right. And BGP, the border gateway protocol, comes as a savior in this situation. Okay. So it is a de facto inter-domain routing protocol. In other words, inter-autonomous routing protocol. It glues the internet. That's very, very crucial. Otherwise, the autonomous systems are going to be staying as separate entity, and it is the BGP which connects them. All right. So BGP provides the autonomous system a lot. I have put some 3 points here. One of them is obtain the subnet reachability information from neighboring autonomous system, that is eBGP, which means suppose I am one of the autonomous systems, you are one of the autonomous systems. Now you may have a lot of computers and networks connected to you. I will have a lot of networks connected with me. Now from this computer, from the network which is within me, from the network which is connected to you, there should be communication established, right? So we seek the assistance of eBGP, obviously the external BGP. All right. Within the autonomous system, among the networks of my autonomous system, among the networks of your autonomous system, we go for IBGP, internal BGP. All right. And BGP also determines the good routes, okay, based on various parameters, but reachability information and majority in major, the policy is playing a key role. Okay, some of the basics. We have a keyword called BGP session. Okay, so two BGP routers exchange BGP message, which means you got this machine called router called 3A, you got 1C. These are the two routers which can be called as peers, provided they have established a BGP session. Otherwise, they are just routers. So BGP peers, they exchange, they shake hands with them, hello to them, and then they start exchanging the BGP messages. Okay, so they advertise the path, and they also exchange the information using the TCP connection, which is also to be noted. We haven't spoken about TCP protocol in the routing protocol so far. Okay, just for instances, okay, you got an autonomous system 3 which is connected to other network, then autonomous system 1 and autonomous system 2. So autonomous system 1 is connected to other network only through either through AS3 or through AS2. Okay, now autonomous system 3 is sharing a routing information to 1C, which means 3A is sharing a routing information to 1C, promising that it will forward the datagram towards that prefix. So when it is sharing, it's not going to share all the routing information. Just hold on. All right. So it's not going to share all the routing information, but it exchanges only the summary or the aggregate route. All right. Otherwise, your routing table is going to be bombarded with a lot of entries, and you cannot even complete your search to find a match when the destination route is requested. All right. So autonomous system 3 in this example, from through 3A is sending the routing information to 1C, that it might have aggregated all these network addresses, and then it promises that, sir, if you have any data to these networks, you send to me, I will take care. Similarly, they would exchange. This is through eBGP. All right. Yeah, that is what explained here. I'm reading the line and then explaining to you using eBGP. Okay, that is external BGP session between 3A and 1C. You got 3A and 1C. eBGP session, you could see the continuous line which is depicting the eBGP. Okay, Through this, autonomous system 3 is sending the prefix reachability info to autonomous system 1. It sends the summary route. It sends the aggregated routing information that you got any packet to these networks, please forward to me. Now, 1C can use IBGP through through IBGP to exchange the routing information to all these 1A, 1B, and 1B, and so on. You also could see 1B is permitted to re-advertise this reachable information to autonomous system 2 or 1B to 2A through eBGP. So very simple. The point you have to drive here is the eBGP information, and IBGP is for the internal circulation. All right. When the router lands a new prefix, if it is new to this, it creates the entry in the forwarding table. Okay, so there are a lot of attributes as I could, you have listened to Mr. Patrick, that BGP uses the attribute as the metric. All right, so advertised prefix includes the attribute. What is that attribute, sir? Prefix plus attribute gives you the route. Okay, what is that attribute? There are two important, I think there are 6 such attributes. I'm not able to recall them, but 2 of them are important. One is autonomous system path. It gives you the continuous or the sequence of routers. Okay, contains the autonomous system through which the prefix advertisement has passed. For example, autonomous system 67, autonomous system 17. So this is going to be a sequence. This is AS path. And next hop will indicate the nearest router. The IP address of the router interface that begins the autonomous system path is the next path. So this is something interesting. You are not having only the routing routers IP addresses, but also the autonomous system number. All right, because it's going to be bigger when the routing is happening in the internet. Okay, the gateway router receiving the route information advertisement uses the import policy to accept. For example, never route something through autonomous system X. So BGP follows policy based routing. For example, you are not permitted to send the internet traffic through this specific country. Policy based routing, BGP supports it. Okay, how does BGP select the best route? Okay, router may learn about more than one route, as in the case of the IBGP, but how the best route is selected, there are 4 steps. One is local preference value attribute policy decision, whether it comes under your policy. Okay, it is all coming, but except these 2. Okay, shortlist. Then which is having the shortest autonomous system path? Okay, this is, but there is a tie. Then who is having the closest next hop router? You go for hard potato routing. Very simple. Hard potato routing is something greedy, where you look for who is the nearest neighbor, use him and keep quiet. Hard potato logic is, suppose very hard potato is given in your hand, you would normally try to give it to other person, and he will give it to the other person because it's too hard to carry. Simple logic. All right, so now you will find out which is closest, hand it over to him, and then if still there is a problem, you can have the additional criteria as decided by the administrator. This I'm not going to store. I'm not going to talk about this, but this is a simple story. All right, now router is aware of the prefix. All right, how is it possible? All right, so BGP message contains routes. We know that route is a prefix and attribute. Yes, we have just seen. Okay, the prefix and the attributes are connected. Okay, these 2 attributes are available. For example, a route could be like this: 132, 138.16.64/22 could be the prefix. .0 is the meaning here. Okay, prefix, and the AS path is one of the attributes. AS3, AS131. The next hop is the immediate IP address. That is the default gateway IP. Okay, so or the next hop IP. So this is an example of route, and hence router is aware of the prefix. All right. So yeah, this is an example. Just I have said it may take multiple routes, but it has to select the one. So best path is selected based on the policy, and then based on the shortest autonomous AS path. All right. Then comes the hard potato routing. As I said, suppose there are 2 or more best inter routes, choose the route to the closest next hop so that you can immediately hand over and get out of this. All right. And the other major one is the policy based routing. We have spoken about the BGP. Okay, an example is given on screen. Probably you can easily understand what could be the example of policy, why policy is enforced again and again and again in BGP. So this is an example given. You got A, B, C. These 3 are these service providers. I do not want to name them. Okay, so this is service provider A, B, and C. You know who is the service provider. All right, and you also have got the customers X, YW, probably WXY. These are the customer network. Okay, maybe Karunya, maybe some other university or some other company, customer networks. Okay, so ABC are the provider networks, ISPs. WXY are the customer. Okay, X is dual home. Yes, X is getting the internet connectivity through B and C. So X is called a dual home. All right. Now X does not want to route from B via X to C. Okay, X does not want to route from B via X to C. Very simple. Now X is the customer network. If B has some data to be forwarded to C, X will not take into this action, because why should I do that? It's not my cup of coffee. I am the customer network. I do not want to take part in your communication. Though I am having the connection, X is not going to accept any such routing information, though it has the connection between B and C. Hence, X will not advertise to B a route to C. X is having a connection to C that will not be known to B. You got it? Simple example, right? Because he does not want to take part in this routing process. Moving on, another policy. A advertises path AW to B. A is the one of the service providers. How much time? Another 3 minutes, please bear with me. A advertises path AW to B. Okay. B advertises BAW to X. Okay. Should B advertise a path BAW to C? No way. Why? It's not required, because B is a competitor to C and C is a competitor to B. B need not tell to C that I have a path through W through A. Then C will not disturb A. It will try to send everything through B, because B gets no advantage by routing this information. Okay, so B wants to force C to route to W via A. Neither W is the customer of B. So B wants to route only to and from its customers. Okay, so B does not want to advertise this routing information to C. So this is another example of policy-based routing. All right, so which is very, very crucial, and you can explore further, and you could see there are a lot of such policies and enforcements are available with BGP. Okay, so fine. So just to summarize, why should we have different intra-autonomous system, inter-autonomous system routing? We can have inter-autonomous system routing. Fine, policy. Inter-autonomous system, admin wants the control over how the traffic is routed. So who routes through its network. But in the intra-autonomous system, there is no policy, because it's all coming under single admin. Scalability, hierarchical routing saves table size, reduces the update traffic. So if there is no hierarchical routing, what is that? Intra-autonomous system. Then between the autonomous system, that is the inter-autonomous system, as we have this hierarchy, the size of the routing table is considerably reduced. And the performance, intra-autonomous system can focus on performance, whereas inter-autonomous system focus on the policy, so that there is no trouble, there is no issue, you do not violate the law of the land. Okay, so that's all I have for you today.